Matthias. I'm working for SAP. And today I want to give you a short history on time. So how are timestamps used in JGit? That's a journey I took this year. So it took a couple of months. I also have some pictures of some famous clocks. So the top one, that's the most accurate mechanical clock known today. It's a remake of a famous clock which won the longitude test in the 18th century when a chronometer was important to do navigation. So it has an accuracy of about 1 second in 100 days. At the bottom, that's the first atomic clock. It has an uncertainty of time measurement 3 orders of magnitude better, so it's 1 second in something like 300 years. Now let's see how this started, this journey. So we had a bug report from, I think it was from Luca. Pack file removed from the pack list, but new list not reloaded. So the starting point is you run a GC on a busy repository, and what was observed is the pack file was marked corrupt and removed from the transient pack list. The effect were missing object exceptions, so JGit didn't find objects anymore which were in this pack. And the only way to fix that was to restart the node. And for Luca, this meant 2 to 3 times a day. When we digged into the code, trying to understand what's going on, pack file name is determined by which objects are inside the pack. And we found that the GC may change the checksum even if the list of objects is the same, if the pack options are different than in the original pack. So this may happen, for example, if a user pushes a pack file, this just ends up on disk, and then you run GC with different pack options. And JGit didn't detect that this file was modified, but it found that there's a different checksum. So it thought, okay, this pack is corrupt, and removed it from the pack list. And this had the consequence that all the objects in the pack file were no longer visible. Then Luca did the first patch, a very simple one, so he moved this line up here. And he added a check for the timestamp. And then Chris commented, we had issues with timestamps, be careful. There's the Racy JGit problem. And I mentioned we already have an implementation called file snapshot in JGit. Why don't you use that? So let's go one step back. How does Git detect file modification? So the naive approach would be to compare the file content, but that's too slow. So what Git does, it compares file metadata, so last modified, size, inode, and so on, which is much cheaper to get from the file system. So that's how it looks if you run a stat just on the file. So you get the size, you get the inode, and you get 2 modification timestamps. And this is much faster. Now let's look at the Racy JGit problem. This is time. Time is discrete on a computer, so we have some resolution of time. And now the file snapshot class is caching the metadata of a given file. So for example, the last modified timestamp. And if we now again look at the same file, do the start call again, and check if last modified is younger than the cached one, then we know it's modified. So this is that case. The 2 times we looked at the file are in 2 different ticks of the timer. Now, what if the cache timestamp is the same like the one I see now? We cannot be sure. So it could look like this 2 different times, but in the same tick of the timer. So we don't know. This is called the Racy JGit problem. This means the finite resolution of the timestamps makes it necessary that in this case we have to compare the content if we only look at the last modified timestamp. And this was what JGit was doing at the time when Luca faced these issues. And as I said, file snapshot was implementing that already. And after this fix, the problem was gone, so Luca was happy. He didn't have to restart 2 or 3 times a day anymore. But then we got a report, there's a performance regression. And the reason was, after this fix was applied, that we observed expensive pack file and indexed rereads. And the reason for that was that file snapshot assumed that this resolution of timestamps on the file system is 2.5 seconds, hard-coded. This is just assuming the worst case, so the file system with the worst resolution is the FAT file system with 2 seconds, and this half second is just some safety margin. So I thought, why don't we improve that? So to detect modification, we considered so far only the last modified timestamp. So I added file size, inode on Unix, and for pack files, I implemented a specialized file snapshot which can also look into the checksum, which is at the end of the pack file. We do this last because that's more expensive than looking at the stat information. And throughout the code of JGit, so far we used millis, which were stored in long. I changed that to use instant and file time, so we can really use the full precision of timestamps available from the file system. So let's look at different file systems. So X3, for example, in Linux has a resolution of 1 second. The more modern file systems, they typically have a resolution of 1 nanosecond. And at the end, you see FAT has 2 seconds. Because of the high variation of different file systems, it may even depend on the version of the file system, what you get. I decided to implement autotuning. This means JGit now measures per file system first the clock resolution by just reading the clock as fast as possible. And the smallest step size I see is the clock resolution. It's worse than real one, but we want to stay on the safe side. Then I measure the file timestamp resolution seen from Java by just setting last modified from the code in a loop and see after which increment I can see the increment when reading back the timestamp from the file. This gives the timestamp resolution. But using that showed up that still sometimes it couldn't detect modifications. So I wrote a test which just touches the file and tries out after which time JGit can detect the modification by using this file snapshot class. And doing that in a loop to get some statistics for 3 seconds. This is some, let's say, 10,000 iterations. We get a second measure for what is the smallest interval we can differentiate. In order to avoid that, we have to do this on every JGit start. This is persisted. Up to 551, it's persisted in the user global git config, and later on it's in a separate JGit config because there are users which distribute their home directory git config onto multiple machines, and this would lead to errors. That's why now JGit has its own configuration file for this data. And now the results, what we found from many tests. So depending on file system and Java version and operating system, sometimes the results were different than what we expected. This partially depends on issues in different Java versions. I will come back to that later. And we also can see that on Mac, we don't need this second measurement. This always gave 0, so the directly measured resolution was okay. But on Linux, it seems like we really need to do a test in order to find out what's the smallest time resolution we can measure from Java. Why this effect? So there are many, many reasons. I'm not really sure what is the leading reason. One problem is that clocks in different cores are not guaranteed to be in sync. Java GC may affect these measurements. Also, measuring the duration of time in Java takes more than 1 nanosecond for sure. JIT compilation may be an issue. The OS task scheduler may have an effect, and in the end, we typically don't use a real-time operating system and also not real-time Java. So that's what we are now doing. We take those two measured timestamps, the resolutions, take the max, and then we add some safety factor for the short times. To be on the safe side, we multiply it by 2.5, and for the 1 second and worse, we just add 25%. So the resulting configuration from the autotuning looks like that. So first you have the host name, in order to prevent that if you copy that to a different system, it's used on the wrong host, because their situation may be different. Then name and version of the Java you're using, and the file system path. Now let's look at Java. If you have a high resolution file system with 1 nanosecond resolution, this is how it looks on Java 8 on a Mac. So everything smaller than 1 second is truncated. It's a bug in Java. On Java 89 on Linux, it's a bit better, so we can see milliseconds. On all Java versions lower than 14, we can see microseconds, but nanoseconds are cut off. Java 14 on Windows, it's still like that, so there's still no bug fix. And on POSIX, it was fixed for a few weeks ago. And another issue we faced is when the Git index had, so on the client side, when the Git index had entries from Git and JGit, we had a mix of precision, because native Git saw the full precision, and JGit, depending on the Java version, a different one. So we now look from the back. If there are 3 zeros in a row, we have to truncate all the timestamps in the index to do the comparison. And then there was a final bug, which looked like it could be also JGit Racy. So we saw errors after pull, that the tracking ref for an update couldn't be logged. And we were chasing for some similar effects like I explained. So the effect was that newly added refs stopped being visible. So it looks like, could be suspicious, it's something similar. And we also saw log failures in one of the Gerrit integration tests. So it looked really like another case of Racy JGit. But in the end, it turned out Hanwen found the problem. Packed batch ref update created unsorted packed refs, so it was a bug in the implementation. And through the high resolution timestamp management I mentioned earlier, this was more likely to happen. Finally, Hanwen fixed that in September. And I hope now JGit has accurate timestamp handling. As a summary, this took 7 months, 82 commits. It was really a long journey. 6 authors were involved, besides me, 5 others. Many reviewers, countless tests on many machines, because it's hardware dependent and it's file system dependent, and Java also depending on the Java version. I did 22 service releases to roll this out. And as a summary, measuring time and detecting modified files seems to be hard. And finally, this is a state-of-the-art clock. So there the resolution is 10 to the power of minus 18. This means 1 second in the age of the universe. Thank you.